work with Bootstrap, which, as we talked about earlier, is a curriculum that combines computer science and algebra. So it's sort of like the zucchini muffins of students learning their math, because they get their algebra while programming a video game. So each part of the video game, there's a part that will correspond to something in computer science, a part that corresponds to an algebra concept that's in a standard algebra class. Unfortunately, we're probably not going to get to program a video game today, but we'll talk about a lot of the tools that kind of set students up for that. So first, a little background on where we are. We're in many states across the country, reaching about 10,000 students. Here in New York, we reach around 2,000 students in 30 schools. If you're interested in some of the information about those schools, ask me after. And that's thanks to CSNYC, of course, that we're here in so many schools in New York City. So I'm going to briefly talk about the theory behind Bootstrap, why we chose to focus on algebra. I'm going to be as quick about that as possible. Then we're going to go over the overview, what the curriculum looks like a 10,000-foot view. And then we're going to do a little bit of practice of pedagogy on a couple of the tools that we think are most important from the curriculum. So before I get started, how many people here have a math background? A few. Okay, and the rest teach computer science? Okay. So I'll be as quick as possible on the algebra part, but why did we choose to focus on algebra when, the buzzword is computer science, computer science? The first reason is it's a major turning point in students' cognitive development. It's actually the first time that students see formal abstraction in an academic setting. The second reason is that the buzzword these days is STEM, STEM, STEM. But what a lot of people don't realize is if you don't get to the part of STEM, you're never going to get to the STE. So it's sort of a gateway to the rest of the sciences. You'll never balance chemical equations. You'll never model projectile motion. You need the algebra before you can do any of the rest of it. Third reason, if you're really cynical and you say, no, it's all about the money, 2004 study showed that the grade in high school that correlates most with your lifetime income is algebra. So if you get an A in algebra, you're much more likely to have a higher paycheck later on, which means that this isn't just a computer science issue or a math issue, it becomes an equity issue. It's ultimately determining the zip code that you live in 20 years later. And if you're even more cynical and you say, no, it's all about standardized tests, what's the standardized test that's keeping principals, administrators, even politicians up at night? Is it the ELA exam? No. It's the algebra exam, specifically the word problems. So for these 4 reasons, we said, algebra is important, that's what we're going to focus on. But as a nation, how do we feel about mathematics and algebra? We're petrified, right? Algebra is terrifying. Walk into any party and start saying this word problem, and you're going to get the same reaction from everyone. Everyone hates it. This is a really hard word problem to set up, and algebra gives us the tools to break it down and make it a little bit more digestible. So, what makes algebra so hard? Why is it so different from the rest of math? Pretend that you, for 5 minutes, are in kindergarten. Can somebody raise their hand, boys and girls, and give me the answer to this thing in red as if you're 5 years old?
Square.
Yeah.
6.
6. And how'd you get that?
I added 4 and 2, and I got 6.
You added 4 and 2 and got 6. Some students might count on their fingers, but either way, you learned there's a process, and that process is going to get you to an answer. You get a little bit older. Maybe you are in 4th or 5th grade now. Could somebody raise their hand and tell me what the answer to the thing in red is?
4.
And how did you get 4? Very good.
I subtracted 2 from 6.
Okay, so you subtracted 2 from both sides. Again, maybe you'll have students that would count their
from both
fingers.
sides. I said
From 6, I apologize.
Both sides.
Yes. So there are many different ways, but ultimately what you're learning is there's a process to get to an answer. Very good. You're a great student. You get a little bit older. Things are going to get really different now. Mind-blowing, right? Can somebody raise their hand and tell me the answer to the thing in red? Sean.
4.
And Sean, how did you get 4?
Start with 2, count up to 6, and
Fantastic. Another process. X is equal to 4. Now you hit algebra. And this is the problem that you get. Can somebody raise their hand and tell me what the answer to the thing in red is? Take a minute and think about it. You're in 9th grade now. No, you don't get called on. That's not fair.
all real numbers.
All real numbers, that's one answer. What do you guys think of that? Anyone have any other ideas? A graph, okay. Anything else? I'm sorry? Ordered pairs. So the problem with this problem is that it's not actually a question, right? There is no answer to this. No longer are you asking students to give you an answer to a mathematical question. Instead, you're asking them to describe an object. And this is the first time that math is completely different for students. It's no longer arithmetic. It's asking them to describe objects. And what makes these objects so difficult is that they're so abstract, we can't even look at them head on. We have all of these different representations for how to look at a function, right? Oops, wrong way. We have the actual equation for it. We have the graph, as somebody mentioned. We have input-output tables, ordered pairs. And we even have mappings of domain and range. And we teach all of these things, or often these things are taught in silos, so it's really hard for students to understand concretely what a function is, and that all of the representations of them are interconnected. So, those are our two goals at Bootstrap. Actually, no, we'll go through this one, we have a little bit of time. So I'm going to show you guys 3 different representations of the same function, and I want you to raise your hand when you can tell me how many roots the function has. Don't tell me what the answer is, just raise your hand when you know. Here's the first representation. Okay, 0 hands. Second representation. I see 2 hands, 3, 4, and third one. I see less hands, but so which is the easiest representation to figure out how many roots this function has? Yeah.
The graph.
The graph. Why is the graph the easiest?
Because the roots are sort of staring you right in the face.
Right.
Before the roots means.
But if you have a high achieving student, likely they're going to tell you, no, I want to see the real function, like the true function. The graph is just what the function produces. So they're probably going to look at that middle representation, which is totally fine. You can get the answer from that. Maybe on a standardized exam, it's a little bit harder to factor. There's a lot of pressure. They make a mistake, but it's still doable. But the struggling students, the representation that they prefer is usually this first one, right? When a student sees a function, they take out a piece of paper, they draw a table, and this is the first thing that they're going to look at. What's the problem with using this representation to answer that question? How many roots does f have? Eric, Sean.
I mean, you in theory would have to guess at like every number
Right.
in existence.
Right.
Like there's no finite process
Exactly.
to get to it, or sort of looking at ordered pairs unless you're like constructing the visual picture, like how you would know when you're getting closer to like narrowing.
It's
it down.
impossible.
Yeah.
Answering this.
There's no process.
Yeah.
I'm sorry?
There's no process.
It's impossible to answer the question using the table. You would have to do it infinite amount of times. So, our goal at Bootstrap is to make these representations of functions concrete and to make the representations of functions interconnected so that students understand what they're looking at when they look at these different representations of functions. So far, so good? Great. Well, turns out programming has functions, right? And so for 20, 30 years now, people have been saying, I'm just going to teach programming and my students are going to learn math. And that's worked out really well, right? All of our students know functions and we can go home. So all of these different languages have been used to teach programming, to teach math. And it turns out that it doesn't necessarily work. And that's because while all of these languages are fantastic, if the job you're trying to do is teach algebra, you need the right tool for that job. And not all of these languages are the right tool to teach mathematics. I'm going to go through 3 quick examples of why that's true. These should be pretty quick because they're all programmers in the room. Math teachers, do you agree that 1 over x times x equals 1 for all non-zero values of x? Okay, 1 over 3 times 3 equals 1. Fantastic. Does anybody know if you type this into Java, 1 over 3 times 3, what the answer will be?
Can you repeat that?
If I in Java write 1 over 3 times 3, what will it return? 0.
Oh yeah.
0. And if I in JavaScript write 1 over 3 times 3, anyone know what that will return? 0.9999999. Neither one of it equal 1. That's our first example. Definitely not the most egregious. Let's try this one. This is Programming 101, super simple, easy program. Can somebody tell me what the value of x will be at the end of this program? 12. Straightforward, right? Raise your hand if you're a math teacher. What's the problem with this?
Equal sign is being used for assignment, and in math,
Not equality.
you want it to be equals.
Exactly. So if I subtract x from both sides here, I get 0 equals 2.
Yeah.
Not mathematical. So equality and assignment are being kind of intermingled here. But it gets even worse. Here's another really simple program. We have a variable foo, they call it a variable. It's equal to 0. And we have a function f which takes in x and then increments foo. Can I have 2 people help me kind of demonstrate this? 2 volunteers? You're smiling, so you're going to be my first volunteer. Sean, you can be my second volunteer. So Sean, you're going to be foo. Joe? Okay. You're going to be the function f. So I'm going to call you as I would a function, so I might say f of 0, and you're going to tell foo to increment, and then you'll tell me his new value.
What do I do?
You're going to increment your value and give it back to f. Tell me.
Gotcha.
Great. So if I say f of 0,
Foo?
increment.
Increment?
1.
1.
1. All right, so f of 0, we got 1. F of 1,
1. Increment?
2.
2.
so far so good. F of 2,
Increment?
3.
3.
fantastic. How about f of 2 again?
Increment?
4.
4.
How about f of 2 again?
Increment?
5.
5.
Okay, so programmatically this is totally fine, right? Math teachers, do you see a problem with this?
So, two twice and got different things.
I said f of 2 3 times and got 3 different answers. So is this a true function in algebra? No, it would never pass the vertical line test. We have more than one output for the same input. But programmers call these things functions when they mean procedures. They call these things variables when they mean parameters. So when you use the same vocabulary in programming and mathematics to do 2 different things, it's probably going to confuse a lot of students, and it's probably not going to be helping them very much. So instead, we need a language that is entirely algebraic if we want to be teaching algebra. If we want to be teaching algebra using computer science. So in Bootstrap, we use a language called Racket. It's a cousin of Lisp or Scheme, lots of parentheses. You'll see a lot of those over the next hour. But the point is that all of the rules of algebra stick in this language. You can't do anything in Racket that you couldn't do with algebraic functions. Again, not to say there's anything wrong with all of these other languages. They're wonderful to teach, just not if you're trying to teach algebra. Okay, so what do we do in Bootstrap? What do our students look like? 70% of them report as being below the poverty line or being African American or Latino. We have 3 main exposure groups for Bootstrap, and actually all of these are represented here in New York City. So either we want to be first exposure to algebra before it actually gets to their classrooms, so grades 6 and 7. So we have a couple of teachers who are using it as sort of a preview before they get to the 8th and 9th grade. We want to, that or be algebra enrichment for grades 8 through 10. So we have some teachers that integrate Bootstrap into an algebra classroom, either as they're teaching the concepts or at the beginning or end of the year. We have some teachers that are teaching a math enrichment elective, and so they'll work with their algebra teacher but teach it in a separate class. And our last option is algebra remediation for grades 11 through 12. So students who have already kind of been burned by algebra the first time around can see it again in a different way and look at those concepts after they've taken the class. Bootstrap materials. So I'll go through this pretty quickly. We provide lesson plans for teachers. We do professional development workshops. All of our software is in the cloud. You guys will have a chance to take a look at that in just a minute. As I mentioned, the language that we use is entirely algebraic, and all of the lessons are aligned to the Common Core standards for mathematics. Any questions so far? Great. So, students will start out in the first lesson of Bootstrap brainstorming their video game. This is sort of the hook for them. And then we use that enthusiasm from brainstorming their game and transition into something a little bit more difficult called circles of evaluation. That's the first thing that we'll look at today. Circles of evaluation are a tool for diagramming arithmetic that happen to translate really well into the syntax of the language. So it allows them to start building their first lines of code. After that, they'll learn about data types and domain and range as it relates to the functions that are built into the language. And then they'll translate that into defining their own functions. And so defining your own functions and animating your game, this is where we start using the design recipe. The design recipe is a tool that allows students to break down word problems into smaller chunks and use each of these chunks to kind of build up to a function. So students don't have to go straight from, reading a word problem to writing the function. They have all of these intermediate steps that they can take to build it intuitively. They'll use these functions to animate characters in their game. Fantastic. We have this enthusiasm again. We'll use that enthusiasm to introduce a new concept of Booleans and inequalities. They'll say, well, this is great. My game's animated and things fly across the screen, but after they go off the screen, they don't come back on. This sucks. I don't want to do this anymore. Well, when should your characters come off the screen if they've passed 0? Use an inequality for that. Excuse me. They'll write a function that takes into account this inequality, brings their characters back on the screen. How many of you guys cover piecewise functions? I know there's only a few math teachers. Okay. So piecewise functions are just event-driven behavior. So they'll use piecewise functions to program their character to move based on different key presses. And last but not least, we'll cover the Pythagorean theorem, write a function to find the distance between objects and detect whether or not they've collided in their game. That's the whole thing. We'll get to like one of these today, maybe 2. Okay, oops. All right, now for the fun stuff. So unit 1, in the Google Doc that's shared with you, there's 2 links. The first is to our materials, so you can check those out, and the second is to WeScheme. So I would go to the WeScheme link right now. I'll log in as well. We're Google authenticated, so when you go to log in, it'll ask for permission. We never see your password, we never see your account, don't worry. Your program list will probably be empty. Mine has a bunch in there already. And you just want to start a new program. So the first thing that we have in this language wouldn't be a good language if we didn't have numbers. So you can go ahead and try any number you want. There's no number too big or too small. A couple of nice features. Fractions, whoops, will automatically convert back and forth to decimals. The program under things stands things like pi and e. So we have a couple of cool mathematical features in there. But numbers are no fun if you can't do anything with them. So take 2 minutes and just play around with the numbers and see if you can try to add and subtract numbers using WeScheme. 2 minutes. All right, so what did you guys come up with? Anyone get it to work? No?
I have a little prior exposure.
Oh.
But it's been like 2 years and I messed around I got it wrong a lot.
I want the example that Sean typed in was open parenthesis 4 minus 5 close parenthesis.
Mm-hmm.
And the error message was able to point to something the language expects. It highlighted that first character and it said, I thought that was a function, but you gave me 4. And then from there, Sean was able to write the expression.
So we're going to come back to what Eric said in just a moment when we learn the correct syntax for this. But Eric's making a really good point, which is one thing I actually forgot to mention. The error messages here are designed to help students. They're not designed to be big, scary red error messages or like sys or bus error that don't really mean anything. They're really useful to actually debug your code. And we'll see more examples of why they're useful later on. Okay, so anyone without prior exposure get this? So we have something called a circle of evaluation that helps us. Oh, my screen is not caught up with here, so if I keep clicking, I'm sorry, I need to look up here. All right, so we want to program 10 minus 8. Let's pretend that our computer is everything inside that circle. Do we know what the answer to everything inside that circle is just by looking at it when it's jumbled up? No, it can either be 2, it could be -2. We're not sure. So we need a very specific order in order to tell which order our number should be in. So we always put the function at the top of the circle. On the left side, we'll put the first number, and on the right side, we'll put the second number. That's pretty straightforward. Now can somebody tell me what the value of everything in this circle is? 2. Very good, Joy. And this structure translates really conveniently to the syntax of the code. So the analogy we use is having an ant walk through the circle. So when an ant sees my circle, the first thing that it has to do is break it in half. When you break a circle in half, what 2 keys on the keyboard does this look like? Parentheses. And after he breaks the circle in half, the ant will always go straight to the top of the circle, straight to the function. After he goes to the function, he goes to the left side of the circle. What do we see on the left? A 10. He goes to the right side of the circle. What do we see on the right? An 8. Not too bad. Let's do a slightly trickier example. So I want to do 6 divided by 2. That one's not trickier. But we said that 10 minus 8 is equal to 2. So what if instead I wanted my circle to represent 6 divided by 10 minus 8? How could I change my circle so that it represents 6 divided by 10 minus 8?
I'm going to take out my HP calculator.
Joe?
I'm going to nest the circle.
Nest the circles. All right, so I said that circle is equals 2, so I can replace my 2 with the circle from up there. And can somebody help me be the ant to walk through the circle and break out the code? Kelly, want to help me out?
Well, we start off with the open parentheses,
Okay.
the operator division, and 6. And I would assume we have a nested, an open parenthesis, minus 10 and 8.
Yeah. So I know there aren't many math teachers in the room, but a lot of math teachers find that they have to review order of operations. So this circle of evaluation, sure, it's a really convenient tool for the syntax of Racket. It's also a really great tool for diagramming arithmetic sentences. It's like sentence diagramming for arithmetic. A lot of teachers will teach order of operations as if it's a computational skill. So give 15 problems with nested operators and then ask for the solution. But that suffers from both false positives and false negatives. If you have a student that says 2 times 2 minus 2 and gets that correct, does that mean they understood order of operations? If they get it wrong, does it mean that they didn't understand order of operations? No, it could be arithmetic errors. So this is a way to diagram that math so that we're taking out the computation aspect and we're just looking at whether or not they understand the structure of the math. A little bit of a side note for a lot of the technology people in the room, but another convenient use of this tool. So just to make sure, so that's most of Unit 1. The other thing we would have done in Unit 1, which we skipped, is the most fun part, which is design your game. So students will sort of take that enthusiasm and we'll parlay it into all of the math that we just did. In Unit 2, students will just do more practice with circles of evaluation, making sure that they understand that structure and they have it down before they start doing more complicated code. So I'm going to have you guys just do on your computer just rounds 1 and 2. Write out the circle evaluation if you have a piece of paper, and then just do a little bit of practice typing in the code for rounds 1 and 2. Take about 3 minutes. Don't do the third one. I just want to have a quick discussion with you guys. Just 1 and 2 with the circles, don't do the third.
The outermost, it can be like in the last one, identifying the innermost is easier than identifying the outermost.
Which just has the beauty of RPN, so that like the top thing comes last. Well, HP calculators are first position.
No, but that's what,
Yeah, yeah. Oh,
not quite.
Well, this is Polish,
Yeah, but-
parentheses.
Yeah.
That's what index, that's what prefix notation.
So I'm going to kind of use the discussion Sean and Eric are having. How many of you guys, when you write these circles, you start at the biggest one and you work your way into the smaller ones? Couple people? everyone else does it the other way, or is there a third way that I haven't learned yet? So whatever you use for the first 2 rounds to write your circles, do the opposite for round 3. Just give it a try and see what it feels like to do it a way that you're not comfortable with. Did you guys notice anything doing it the way you weren't comfortable? Do you think one way is better than the other? Yeah.
I just think if it's only 2 operations working outside in, it has to be reflex.
Okay.
But when you have 3 operations, I think that you just need inside out.
Okay, so the more complex it gets, it sorts of change the way you're thinking about it. Anyone else think that they've got the right way to do it? It's the best way? No. It doesn't really matter whether you work inside out or outside in. As you said, it kind of works differently depending on the problem. It's important that students see that it can go both ways. They might find that one is more useful to them and one makes more sense. But ultimately, it doesn't matter. It's just nice for them to see both.
Quick question.
Yeah.
In terms of, in terms of teaching students, when we talk about order operations, especially when actually the second and third example, they point them to the parentheses first, so we should create that circle first. Is that
So in a math class, a lot of teachers will have these without the parentheses, because the parentheses are sort of like they're a hint, right? So for the purposes here, we have them, it just makes it a little bit simpler. Many math classes won't have them at all. And so circles aren't going to magically bestow the knowledge of order operations on your students. There's nothing inherent in them that says PEMDAS. But they do allow you to test whether or not students understand that order, or whether they can just do the computation or not. So there's nothing like magical about it that gives you the order. It's just a matter of diagramming it correctly. Does that answer your question? Yeah. Do you have a question?
Does the computer evaluate outside out or outside in? Is it possible to say?
So computer evaluate outside out, outside in. Inside out. Has to be inside out, right? No, it doesn't have to
No,
be.
I think in a functional language it doesn't matter.
Okay.
It's
Like, I mean, the
but
idea
it's
is
actually both. It's like it attempts to evaluate the outermost,
Until it hits something it can't.
and then which requires it to evaluate each of the arguments of the outermost, which would then require it to evaluate all the arguments inside of that argument. So then it'll start returning values from the inside out until it can finally evaluate the outside.
So let's just do a little bit of practice of converting this back to code before we start coding things. So can somebody help me with the first one? How would my aunt break apart this circle? Yeah.
With the, you want me to tell you what it is with the parentheses?
Yeah.
Okay, so I think
Step by step.
Open parentheses, then a subtraction sign, then another open parenthesis, multiplication sign, space 3, space 7, close parentheses, open parentheses plus space 1, space 2, close parentheses, close parentheses.
Great. How are you guys feeling about the circles and the syntax? Do you want to do a little bit more practice, or? Okay. I don't want to dwell too much on this. There are more exciting things to see. So I'll put these up just for a moment if you want to check your own work. Round 4 is there for homework, so you do that on your own. Okay. So after students have the basics of circles of evaluation, they can write basic arithmetic pieces of code into WeScheme. We move on to contracts. So how many of you guys know what a function machine is? Or use it in your math class, right? So a function machine is some sort of black box. We know what goes in, we don't know what comes out, we don't necessarily know what happens in between. So the way that we keep track of our function machines is by using something called a contract. The contract keeps track of the inputs and outputs. Every contract has 3 parts. The first is the name of the function, pretty straightforward. The second is the domain, what the function is taking in, and the third is the range, what the function is giving back. This is really familiar math terms in computer science. Maybe it's a type specification, or there's another word for it. Signature. Same thing though. I totally came across this once. So I have a function machine that I really like at home. It came in handy this morning. It is called Mr. Coffee. So Mr. Coffee's domain is coffee beans and water, and its range is hot, delicious coffee, as long as I obey my contract and give it beans and water. What's really important about the domain and range is that we're talking about types, we're not talking about examples. So I don't have to give Mr. Coffee like Starbucks anniversary blend beans and filtered Fiji water. I can give it any coffee beans and any water. It'll still give me back coffee. Maybe not as good coffee, but still coffee. This becomes important when we start talking about mathematical functions. So, for example, plus takes in 2 numbers and returns another number. Plus doesn't take in 3 and 5 and return 8. 2 numbers returns a number. So what we have students do in their workbook is keep track of all of the contracts that they learned for functions that are built into WeScheme. So this is the point where I'd have you turn to the back of your workbook and start filling out that log. And that log becomes a cheat sheet for them for the rest of the course. Anytime they're not sure of what function to use or they're not sure how to use a function they know they need, they can always refer back to that and see what their options are. So some of the other functions we'll keep track of. Subtraction takes in 2 numbers, returns a number. Square root, affectionately known as squirt, takes in 1 number, returns a number. It can take in negatives. Computer does understand imaginary. And square takes in 1 number, returns another number. You guys can give a couple of these a try. I'll give you a minute to just play around with some of the new functions. Those of you that are using phones, you can use WeScheme on your phone if you'd like. Do you guys have a chance to try this out? What do you think? Any questions? Yes? How would I, one of these?
Okay, well, values between.
So for example, square root 25. Okay, 5. The circle of evaluation for that would just have the square SQRT at the top, and then its only input would be in the middle. There is no left or right for that.
I was just
All right.
I wanted.
So those are all our functions that take in and return numbers, but that's kind of boring. The language gets a little more exciting than that. We also have functions that take in strings. So everyone here already knows what a string is, anything inside quotation marks. And some of the functions we have that take in strings, the one on the bottom. So can somebody tell me what the name of the circle of evaluation, the function the circle of evaluation at the bottom is?
Star.
Star, how'd you know that?
It's
It's at the top of the circle.
It's a good ant.
He's a good ant. What's the domain of the function star?
Number and 2 string.
Number, string, string. And what if I told you the name of my, I'm sorry, the domain of my function was 50 solid red? What would you tell me as a student? If I said that the domain for the function star was 50 solid red.
What would your answer be as a teacher to that student? Is that your question?
Yes.
Yes.
That's just an example.
Yeah, it's one of
Yeah.
possible domains.
Those are examples. The types are 50 is a number, and solid and red are strings. Okay. So with your partner, convert this. So what do you guys think the range is for this function? What do you think it's going to give me back? We don't know yet, so just take a guess. A red star that's 50 something. That's one option. Any other guesses?
The range,
Yeah.
shape.
A shape. Yeah. Some students will say it'll give me, 50 red stars. Some students will say it'll draw the word star. So it sort of varies. With your partner, type in what the code would be for this circle evaluation and figure out for yourself what the range of the star function is. All right, so what would you find out? What's the range of star?
Star shape.
It's a star shape. So it's an image. So we suddenly have a new data type. We just learned about numbers, we learned about strings, and now we have images too. There are a bunch of functions that return images. We have circle, which takes in a number, 2 strings, returns an image. We have ellipse, triangle, rectangle, and then last but not least, students really like the function text. Text just takes a string and turns it into an image. For some reason, even though students have seen their names written thousands of times, but before they've seen this, seeing their name written in the text function is totally different. So again, this is where we would have students write out all these contracts in their contracts page. There are going to be times when we need to refer back to them. You guys don't have a contracts page. So instead, take about 5 minutes to play around with some of the image functions. Try text, write your name in text. It'll be like mind-blowing. Okay, so we have these images. use some of these functions to put images into their game. Again, you guys get to skip the fun parts, so I won't be doing that. There's a supplemental lesson at this point that a lot of teachers use. It's flag building. So I'm not sure if Eric has used this, but basically, especially in New York, we have classrooms that are made up of 30 different nationalities. And so students can use all of these functions along with a couple of extra image manipulation functions to actually build the flag of their home country. So we have a lot of really amazing work from classrooms all over the city where students have done this and try to make each one more efficient than the last one and use shortcuts and things like that. So it actually becomes a project in and of itself, totally separate from the video game. We could talk more about that after if you'd like to see some examples of that. All right, so we're power houring through. We've learned about Unit 1, Unit 2, circles of evaluation, domain, range, image functions. Time to get to the fun stuff. We're going to finally talk about the design recipe. Before we move into that, I know that I really rushed through this first 2 units. Anyone have any questions or things they want to go over before we move on? So, I feel really comfortable with you guys. In this past 45 minutes, I feel like I've really gotten to know you, and I'm going to share a really dark secret. My favorite shape is green triangles. I love green triangles. So can you tell me, how would I make a green triangle? How would I type it in? What code? If I want to make a green triangle solid that was 50 pixels. I know you guys don't have a contracts page to refer to, but okay. So, but using the functions that we just learned.
There's a triangle function?
There's a triangle function. So let me pull this up again. Not the best stand-in for a contracts page, but it'll do for now. All right. So if I wanted to make a triangle that was 50 pixels solid and green, what would I type in? Parentheses.
Triangle, space 50, string solid, solid, and string green,
Okay.
green.
Beautiful. There goes my green triangle. But I said I really, really like them, so what if I want to see another one? How would I make one that's 100 pixels big? That didn't work. How would I do it?
Triangle 100.
Rewrite the whole copy paste.
All right, so triangle 100, solid green. Beautiful, but I really, really like green triangles. Now I want one that's 150 pixels.
Type it all
Can
again.
you define?
Type it all. Okay, so obviously
Can
this
you
is intentionally
define
frustrating.
Number to be
And
X?
I'm sorry?
Can you define the number to be X?
Close. Very close. So we're getting there. We want some sort of shortcut to make this triangle, right? I don't want to have to type in all of this code over and over again. And you'll see some classes that are really patient and will just tell you how to write the code for every single size you give them. And some classes that are like, okay, I'm done with this. I don't want, like, whatever game you're playing, I don't care. So it depends on who you're working with. But we want to be able to just have a shortcut to this function, sort of like defining something. So I want to define a function called GT, which will just take in the size, because I know that it's always going to be a solid green triangle. GT takes in a number and gives back a solid green triangle of the given number. Now, instead of going straight to defining the function, we're going to go through the design recipe, which is a process that breaks down that function definition into 3 different steps. The first step you already know about, it's the contract. So what are the 3 parts of a contract? Name, domain, range. What's the name of the function I'm trying to build?
GT.
GT. And what's GT's domain? It's a number. And what's its range? What's GT going to give me back? A shape, an image. The data type we call as image. Okay? Can I have a volunteer to help me act out GT? Sure. Okay. So I'm going to call you. I'm going to say like GT 100, and then you're going to do exactly what we did before. You're going to give me back the code that you would use to make that triangle. Okay. So if I say GT50, you'd tell me,
Triangle 50 solid green.
perfect. GT100,
Triangle 100 solid green.
excuse me. Yep, so this is exactly what we want. The next step in the design recipe are 2 examples. So in mathematics, this is sort of the equivalent of the input-output table. In computer science, this is unit testing. We want to look and see what our code is supposed to produce before we actually write the function to produce it. So GT, if I say GT10, what will you give me back?
Triangle 10 solid green.
Yeah. It's important that on that second line, we're showing the work that we use to get to the answer, that code we wrote, not just what the answer is, not just what it produces. And if I say GT11,
Triangle 11 solid green.
thank you, GT. What's important is that each part of this example came from the contract before it. The function name was in the contract. The domain, it told us we needed a number, so we could give it any number. And then the image, we knew that we were going to create a triangle. We just need the code that we use to create that triangle, which you would get from your contracts page. So we're building on all of these tools that we've previously learned. So we have our contract, we have our examples. The next part is the part that every adult and student forgets. We want to circle and label our examples before we move on to the definition of the function. So the parts that we circle are the parts that are changing. Which parts change from example 1 to example 2? What's different? Which parts specifically of the domain and range?
The number.
Okay, so 10 and 11 were the only 2 parts that changed. And what do you think a good label is for 10 and 11? What does it represent?
Size.
Size. What's a synonym for the word changeable? Variable. So 10 and 11 are our variables. Size is our variable. So now we're getting to what a programmer calls like the hardest part of defining a function. It's actually writing that last line of code that does the work, that creates the triangle. But the truth is, if you've done all of the design recipe up to here, this becomes the easiest part. Because the only thing we're going to do is copy down the parts of our examples that stayed the same. And the parts that changed, we're going to replace with the variable label that we put in our examples. So GT, what should I do? Should I copy that down or change it?
Copy down.
Copy it down. What else should I copy down to the next line? Triangle solid green. GT, triangle solid green. All of that stays the same. And where I had a 10 and an 11, what am I going to put in my definition instead? Nice and loud?
Paired.
And what's that?
Size.
Size. And my work is done. Not so hard because I had the examples to base it off of. Take 2 minutes with your partner to type in all 3 parts of the design recipe into the definitions window in WeScheme. So that's the window on the left-hand side of WeScheme. If you hover over it, you'll see it says definitions. Not fantastic. That's where you want to type in your contract with a semicolon in front, that means comment, your 2 examples, and the definition. All right, so I have all of my code written in here and I press run and I made a mistake. I press run. How come I didn't get a triangle when I pressed run?
You didn't call the function.
I didn't call the function. So, how would we call the function GT? Pretend it was in a circle of evaluation. I heard Sean parentheses, GT,
1,000.
1,000, okay. Close parentheses. So big I can barely see it. And that's it, we have our function. Let's do one more example of the design recipe. I actually lied to you guys. You can see my lie already.
Rosanna, I just wanted to ask you, you probably are probably going to say this later, but are you going to say what example was doing and what happens when an example
It's right.
breaks? You'll show that later
Yeah.
on.
I was waiting for someone to ask me if we needed to type in examples, but you guys are all either obedient or just didn't do it and didn't tell me. So let's talk about that now. Okay. So if I don't write these examples in, do you think my code will still work?
Yes.
Yes.
Did you guys not write your examples in?
No.
All right, so it still works. If I write GT50, I get my triangle. However, if I break one of these examples, let's say I said GT10 is going to return a circle, 10 solid green. I made a mistake in there. The computer is going to tell me that something's not quite right. So my code will still run. It's still going to do whatever my definition said to do, but it's going to give me a hint that I probably made a mistake somewhere. And if I click my check expect error, it highlights exactly where my mistake is, and it tells me that the actual value image differs from the image the expected value. So it's telling me that I said GT10 would do one thing, and it actually did something else. It didn't return a circle, it returned a triangle. So it's catching your mistakes and telling you where you should kind of double check them. So the examples are useful because it'll help you to A, build that definition, and B, error check you. If you don't have them in there, it still works, but it's important because they do help a lot.
I call it getting customized error messages. Like we want a personal error message. Not
For
just-
exactly
not
where
just a
your
general
mistake
error
was.
message. I want a personal message from it. And that's why you write it down.
So I know it's easier to skip them, but they're actually really important and helpful. All right, let's do one more design recipe. Maybe even two. So I lied. I actually really like blue circles, which is true. I like the color blue a lot more than the color green. So now I need you guys to help me write a function called BC, which will do the same thing. It's going to create a blue circle that's solid, and the radius will be whatever radius I give the function. So again, where do we start in the design recipe? What's our first step? Yep, the contract, name, domain, and range. Can somebody up here help me out with the full contract for the function BC? Sean,
Name is BC.
okay.
Domain is a number, and the range is an image.
Beautiful. So far, so good. Now I need to write my examples, and I'm not sure where it goes in that first line of my example. Where can I look? Where can I look for a hint?
Previous codes.
Next line?
Previous codes.
Do you mean GT or do you mean something on this screen? Okay, so we could look back at previous code, but I want to do it based on just the design recipe. I want to use things I've already written to help me build my examples. So if we had a workbook in front of us, that first line would actually say function name underneath it. Where could I find my function name in the design recipe? In my contract. So I know that my contract tells me my function name is BC. And if I'm not sure what to put on that second line, I'm not sure what BC takes in, I can look at my domain. My domain says BC takes in a number, so what number should I give it? 8. I heard 16.
At least it was a multiple.
All right. So when I say BC 16, I don't know what to put on that third line. Where can I look for some help? I can look at the contract. The contract says an image. And what if I didn't know which image function to use? Where would I might have a list of all of my image functions? In the back of my contract log. I know you guys don't have that tool right now, but that's our kind of backup option. We go to the back of our contracts. We know every single option available to us. So BC16, what code would the computer use to write BC16? Think back to your imaginary contract log.
Circle 16 blue solid, something like that.
Now if I say BC 99, I'll get circle 99 solid blue. What's my next step before I move on to the definition? What should I do? It's the part that everyone forgets. Oh, highlight what changed. Highlight what changed. So Kelly, what should I highlight in these two examples?
The number 16.
99. And somebody else, what do you guys think a good label is for this? Size, what's even more specific than size?
Radius.
Radius, yes. Size is perfectly fine. We want to be as specific as possible though, so I'm going to choose radius. And now that I have these circled and labeled, what's my last step? What should I do in my definition line?
Copy paste.
Copy and paste. What should I copy down?
So that hasn't changed.
Okay, so I'm going to copy BC, circle solid and blue. And then in place of 16 and 99, I'll put the variable name that I labeled. So radius. Are you guys all typing this in? All right, so take 2 minutes to put in the entire design recipe for BC. Try breaking an example and seeing what the feedback is and how that's helpful. And then just try using the function BC. Capitalization does matter. So define as all lowercase, an example is all capital. So we only have a few minutes left. I'm not sure we'll have enough time to move on to a more complicated design recipe question. I'm going to show you guys briefly what it is. The next unit, students will start to write functions that will animate things on the screen. So we give them this word problem that is actually comes straight off of a standardized algebra exam in Massachusetts. And the word problem is supposed to return the height of a rocket after a given amount of time. We've actually put together a teach pack that has an animation of a rocket. So students will fill out the design recipe in their workbook and then program in the function for the height of the rocket and use that function to make the rocket blast off. So then they can add acceleration, they can add gravity, you can do any kind of function you want after you do the initial linear function. So there's tons of ways to expand it, and it kind of makes this idea of writing functions more concrete. They actually see the output of the function as the rocket moves. So if anyone wants to hang out after, I can show you guys that example. I don't think we'll have time to do it all together. There are a couple of reasons why we find the design recipe really useful. The first is that you no longer have to answer a student's question. You can always ask another question. So it's a really good pedagogical tool. We saw a little bit of this when I was asking you where to get things for the next part of the design recipe. You can always say, well, if a student says, I don't know what goes here, you can say, well, look at your contract. What does the contract say? If the student says, I don't know what my variable name is, you can say, well, what did you circle and label? If a student says, I don't know what to give my function, you can say, what does your domain say? So there are all of these questions you can ask to help them build the answer themselves instead of ever giving it to them. It also helps you to debug their thoughts instead of their code. So if you go straight from a problem to a function solution, you don't necessarily know what happened in between. And there are a billion different ways that they could have made a mistake to get an incorrect solution, or even accidentally got a correct solution. But if you break down each of the steps, it allows you to see what went wrong where and possibly why. We have a lot of examples of buggy design recipes that kind of reveal whether a student didn't understand how to find the area of something or didn't understand the difference between radius and diameter. Those can all be mistakes that happen in one problem that lead to an incorrect solution, but it's kind of hard to tell which one it was. The third reason is it's a confidence builder. So for students that are having a really hard time getting straight from word problem to function definition, that's a huge leap. They can instead make one tiny step, which is writing out their contract. And then once they've got their contract down, they know that they definitely have enough information to get a little bit further to the examples. And once they have the examples down, they know they definitely have enough to get all the way to the definition. So it breaks this really massive problem down into all of these really tiny steps that are easy for students to digest. So it helps them to know that there's no reason they have to go all the way to the end. They can do it piece by piece and get there eventually. So with that, I think we only have about 5 minutes left. Any questions on the hour of 3 units of Bootstrap, which is normally about a day of a workshop? Yes.
How long is the entire curriculum? Is it meant to be done over an entire year?
It's about 25 hours of material. Teachers will do it in different ways. So a couple of teachers in New York City are doing it kind of integrated throughout the year. So when they teach linear functions, they'll do the design recipe and then they'll go into that rocket height example that I just talked about. When they teach piecewise functions, they'll do the Bootstrap piecewise functions unit as well. That requires the most planning, obviously. What a lot of teachers will do is maybe 2 weeks in the beginning of the year to either review concepts or preview concepts, do like a Bootstrap unit, or 2 weeks at the end of the year also do a Bootstrap unit. It's also helpful if you're not teaching a math class, if you're teaching like a math elective or a technology elective, because then you can kind of coordinate with your algebra teacher and teach the relevant concepts, but you just have more time. Eric, what was your model? You were teaching it in a computer science class?
So I've done a couple different things. I have done Bootstrap in an algebra class as an algebra teacher, where I'll do it for a module, which I've done it just start to finish. But I think doing it kind of interspersed could also work, but I haven't done that. I've taught a 1 semester elective to 9th graders that's the same concepts, but taking a long time and going deep so that they have time to practice with a lot more of the primitives. And I make a really big deal out of the flag project. So that's like a midway, and I have them do some research about the symbolism of their flag, and then take it a little step farther, so it's not just hard-coded one-size flag, but it's a parameterized flag that can be any size. And a lot of that comes from the construction diagrams that can be found if you research the flag. Like the geometry of the flag of the United States is part of our federal code, which is so interesting, and then you can turn a law into a program, and that's really cool. So that's a single semester elective, and then I've taught, and I'm working on developing a full year computer science principles course based on Bootstrap pedagogy, where they go beyond this and they work with lists and recursion, and they can and data structures, and they're able to build their own simulations and video games and things.
So that's the Bootstrap 1, and then we have a Bootstrap 2 curriculum that will transition students from Racket to a language called Pirate, which is sort of a functional Python that's not white space sensitive.
But semantically it overlaps with Racket, so they get this. If you taught in Racket, you can switch to Pirate, and the images all behave in the same way, but syntax is different, and it just gets them to, it breaks them out of pattern matching and into really thinking about how functions behave. And I've seen that as an extremely powerful switch that you can make using Bootstrap.
So that Bootstrap 2 curriculum is much less algebra and much more computer science. Goes into data structures. With Bootstrap 1, when students program the video game, they basically get a teach pack, and they have to fill in each of the functions in the teach pack. With Bootstrap 2, there is no teach pack. Students are creating that teach pack. So for a computer science class, the transition from Bootstrap 1 to Bootstrap 2 to eventually a CSP full curriculum makes more sense. Yeah.
Do you have an example of the...
A full game?
Yep.
Yeah. Let's see. I break them a lot during these. Let's see. This one should work. This, I believe, is from a class in Chinatown at PS 126. So, I think I'm supposed to avoid, no, maybe I'm supposed to get that guy and lost. But one of these is a danger, the other is a target. These lines that you see drawn, those are optional. That's part of the distance formula unit. Students, before they program the distance formula, those will say 0 on each side, on the hypotenuse of the triangle. They have to make it the correct number. And then they can get rid of them, but the student chose to leave it in. And when I hit 0 points, I lose the game. But linear functions are making their characters move across the screen. A piecewise function makes my player move up and down when I press the keys. And there's an inequality that detects whether or not things have collided. and inequality to detect whether or not my characters are off the screen and should regenerate back on the screen. Any other questions? Yeah.
What's next to full day PD here?
Great question. So the DOE is doing a STEM Institute over spring break. It's a 3-day workshop and 3 days of follow-up in July. And you get per session for it, which is great. There's also CSPD Week in Denver, which is a fully funded week-long PD. So travel, stipend, and PD are all free. I can send out the information for that. I think it's July 18th to 22nd in Denver. All right. Thanks, guys.